You hear me? This is good. Okay, while I didn't start my talk yet, let me take a selfie with this amazing audience for my mother. She really likes this type of the pictures. Okay, let's do it. Mandatory like thing. Okay, so can I start, or we're still waiting for more people to join us? Yes? No? Okay, let me start because it's already time. My name is Vladimir. I work as a senior computer vision engineer at Lyft Level 5. What is Lyft Level 5? As many of you know, Lyft has two main divisions, if you want to think. One that makes money, right, sharing one. You know, we all, or most of us, use Lyft here in the Bay Area. And second, that spends money, self-driving division. We develop autonomous cars. It's long-term bet, and that's where the most exciting problems, in my understanding, are, especially if we are talking about computer vision. I have some experience in machine learning competitions. Many of you know this platform Kaggle. I participated in a few, especially computer vision challenges there, and got the title of Kaggle Grandmaster, which helps me in my job, but it's discussion for a separate time. Okay, as many of you see in the agenda and maybe on the website, it was something about HD maps, autonomous driving, things like this, but I will not talk about this today. The reason for this, because getting approval inside of our company from marketing, legal, comms, and other departments about talking about something that happens inside of the Lyft is extremely challenging. And that's why today I will talk about something slightly different. I'll talk about image augmentations for semantic segmentation and object detection. It is Computer Vision Summit and still kind of relevant. Okay, the reason for this is in my free time I develop a library for image augmentations. It's called augmentations. It has some adaptation within the community. You see 4.5 started at the GitHub, and it's part of the PyTorch ecosystem. If you go to the PyTorch website, there's an ecosystem, and it has most popular packages that are built on top of PyTorch. We are one of them. It also used in academia. Yesterday I checked, it was 43 citations. This number is growing. And again, if you look for computer vision competitions at Kaggle and other platform, most of the winning solutions used our library and used these tricks that help to get to the top. So in this sense, it's a powerful technique. And in this talk, I'll talk about more details, what augmentations are, why do we need them, how it can help you to save money, and why it's a mandatory trick for any computer vision pipeline. Okay, so computer vision tasks, there are 10,000 different computer vision tasks, especially these days when industry in the domain of computer vision became mature. But if we talk about those that are used in industry to map data into money, and more or less widely spread, it's typically image classification, detection, segmentation. So here in this slide, I'm just recalling you, reminding what it is. If you have some input, some kind of image, and as an output, you want some kind of semantic meta information. Can be label, can be one label, dog, cat, or maybe multiple of them, human, sheep, dog. More fine-grained bounding boxes, again, extremely widely used in self-driving industry, and many of tasks that I'm working on related to all these three tasks, and semantic segmentation or instance segmentation, where you go even more fine-grained, and you do this on the pixel level. Okay, so it was general introduction. Right now, if you read some blog posts or maybe come to some meeting on some conferences, people talk about data is the new oil, more data you have, your life is better. In some sense, it's BS, but not completely. To some extent, it is right. There are interesting thoughts about how to maintain growing data that you collect, how to create more labeled data. But overall, from the experience, from the experiment, we know there are different ways to improve your machine learning models. And we can think about two sides of the spectrum. On one spectrum is research approach. Let's say you have fixed data set, I don't know, ImageNet or Open Images or Vistas or Cityscapes, and then researchers publish their works at different conferences. They try to build models that work better on this given data set. And different types of the techniques, network architectures, training pipelines, schedulers, optimizers, all these things they develop. This works to some extent. At the same time, many companies in the industry, they realize that it's not reliable. I mean, there's research team, you tell them, okay, guys, that's our performance for our model. How much time do you need by Friday to improve it by 10%? They're just it may work, it may not. Machine learning is an alchemy, there is no guarantee on this. And again, Andrei Karpathy had pretty good talk about this. How can you do it with the data? So if you have some model, you have some training pipelines, you throw more data into this, more data you throw, better accuracy of your model. You don't need to do any improvements in terms of schedulers, augmentations, any other tricks, but still kind of works. The issue is that improvement in your model accuracy is logarithmic. I like this example. There was some paper in which people took ImageNet and they got some model, they got the accuracy 81% of one. And then they parsed, I believe it was Instagram, and they got 3.5 billion labeled images, and they trained exactly the same network, and they looked at the accuracy of this result, and they got 84. So yeah, for sure, it was an improvement. They got from 81 to 83, but they labeled their labeled data set improved 1,000 times. So getting more labeled data is a pain, but still should and can be done. That's why many companies that I'm looking for and talking to, they're focusing not in terms of let's hire more people with PhDs and research scientists and read more papers, but about building machine learning infrastructure to get more labeled data, to get more relevant labeled data. And again, we've seen a lot, there's explosion in number of companies that work on building some on labeled data for you on demand. Okay, so what are the difficulties with labeled data? You need to collect this data. I mean, I work in the self-driving. This may be challenging, especially because, I don't know, you collect data in summer and then you need to apply this in winter when it's much more dark. What will you do? You need to collect more, and it's again, costs some money. You need to label this data. For self-driving, it's maybe not such a pain, and again, if you need to distinguish on images, dogs versus cats, it's also kind of doable. But let's say we're talking about X-rays. There was one project I worked on. There was some X-rays, and you need to build some classifier to detect what's happening there. Basically, yeah, let me still continue picking. So basically, I worked on some projects. So typically, I like to look at my models. I like to look at the images. I like to see where my models are mistaken, what is wrong, and to get some visual feedback and improve models that I'm working on. But I was working on the images where I needed to detect pneumonia. I have no clue. I look at these X-rays, and which part of this image do I even look for? Are there bones? Are there lungs? I'm not an expert in this. To do good labeling for pneumonia and other, some medical type of the imaging, you need experts, you need doctors. Problem number one, doctors are expensive. Problem number two, they don't agree with each other. So you send same image to 5 different doctors, you get 5 different answers. There are a lot of discussions about CRX14 data set, where Andrew In and his team trained state-of-the-art models, as they claimed, and then people realized that half of the data set had wrong labels, and it's unclear what exactly did they learn. But yeah, basically medical imaging is a pain. Again, coming back to medical, privacy, and legal issues. And in self-driving, tech is not entirely here. If it was tech was here, models were here, we would have self-driving cars on the streets. Do you have them? Maybe in Vegas, you can order a lift and you get self-driving car there. Maybe in Phoenix, you do something and some car with 2 dudes there that behave that they don't exist. There's some safety engineers come to you and can drive you somewhere. But still, self-driving tech is not there. For medical imaging and many other tasks, it's here. We can do it. Technology is here. We can save life. We can make money. Market is big. Life is good. But FDA's approvals and a lot of privacy and legal issues. That's why when I was working on some problems, in this case, machine learning competitions about medical imaging, I remember one of them, my trained data set was 40 images, my test data set was 100 images, and I needed to build some robust solution based on this. Why? How? I was told that no more data is available. Again, so getting more data, labeled data, is a pain. Okay, so there is a trick. There are many ways to deal with lack of labeled data. The best approach is to get more labeled data, but there are still some numerical techniques that allow you to mitigate this issue slightly, at least to some extent. So I'm talking right now about image augmentations. What image augmentation is? Image augmentation is a transformation of your existing data that kind of makes sense and doesn't move you that much from the original data distribution. So here's an example here for image classification. Here's your parrot on the left, and then you can flip it, crop, play with your pixels, do something else, and this is standard technique. It's typically used, some slight augmentations are used for different research and different industry, but what I'm trying to emphasize in this talk, one can go deeper. Okay, so image augmentations are Why do you need image augmentations? As I've said, you need to increase this. You can think about image augmentations as an increase in the size of your train set. Again, if you have a bunch of images and you need to distinguish dog versus cats or pneumonia versus not pneumonia, I mean, flip it horizontally, you get like twice bigger data set. It's not exactly twice bigger because there's big correlation between original and transformed, but still kind of works. And if you do slight rotations, you play with pixels, this number goes up. So you can think about synthetical increase of the size of your data set. Second one, you can make networks invariant to the perturbations of the input. So if you have some data set, it follows some distribution. Again, let's think about self-driving. You got like your data in, you have some small data set and you train some model. I mean, you do some predictions, maybe not that robust, like really. Let's restate it. Let's say you train some network on some small data set, you look at these predictions, looks good, then you maybe slightly adjust this data set, you train the same network and your predictions are really different. So it tells that your network is not really robust in many ways and you wanted something more stable, small variations in your predictions. And so again, you add these like augmentations, it kind of like boosted the size of your data set, your networks become more robust. I like to think about this from the scientific point of view, theoretical if you want. So augmentations is a regularization, same as L1, L2, batch norm, dropout, but it is interpretable one. You can look with your eyes what you're doing. For batch norm and dropout, you look at this constant that we like learn during training, 1.2 in this constant for batch norm. Is it good or bad? Like you don't know. But for image augmentations, if you had some normal people that has pink skin and then you do some augmentations and they become purple, maybe it's like overkill. So you get some feedback about this. And what is the most important, and there is active area of research about this, when we were studying machine learning in universities, we were told, okay, take some data sets, split this into train and val set, and then they should have exactly the same distribution. You train on one part and then predict on another, and your life is good. You publish a paper, it got accepted to NIPS. This is true. Sure, it works in academia. Then you try to do it in industry, and you now have the situation, because like data set that you have, again, if you're talking about medical imaging, data may be collected in one hospital on the like devices that were like built in 1990, and then you apply on some other devices that we built in 2015, and it doesn't work that well. So train and test distribution are different. There's like also time shift. Again, good example about self-driving. You may collect some data in summer and you train your models, and then winter comes and you start driving in the evenings and you don't detect traffic lights or something else. Why? Because still traffic light, but you were not ready for this like slightly darker images. And image augmentations, they help to address this issue. Not fully, still adding more label data is better, but at least slightly. Okay, so you may think about augmentation in this way. You can think about augmentations as a tool to add more accuracy. Again, machine learning competitions, and with one use case, you have some fixed amount of data, and then you need some techniques to boost it higher. You have some network training pipeline, you add correct image augmentations, and in this table, probably I should do this as a plot, go from left to right, same network. Simple augmentations, a bit more advanced, and then on the right, like some more recent paper. And as you can see, same data set, same model, you get better accuracy. Sure, this improvement may be not enough, but we are still talking about improvement of something that was like optimized and overfitted to ImageNet for the last 10 years. And again, in some things like self-driving, where price of mistake is maybe someone's life, or maybe medical imaging, where again, price of mistake also falls in this domain, this may be important. Okay, one of these augmentations that were kind of mentioned in the previous slide is called auto-augment. Really like this paper. It's one of the examples when reinforcement learning was useful. People talk a lot about reinforcement learning, but number of use cases for it, like it's not that wide yet. So for this paper, people took some kind of augmentations and used reinforcement learning and got even some weird transforms. You see on the left is the region, on the right something like resembling it, but slightly different. But they got very robust and accurate models. Auto-augment is a pretty good trick. And as you see, like some castle, or maybe tower, and something is happening with it. Next slide. This is again closer to business and product use case. Again, active area of the research. Let's say you have some data set. Let's say this data set is big. Let's say you have some model. And let's say the accuracy of this model is good enough to be deployed to the mobile. Accuracy is good enough, I mean, satisfies your business use cases, but you want to deploy it into the car or maybe, to like cell phone or some other embedded devices, but model is too heavy and it's too slow. And so accuracy is enough, but model is too heavy. There are like a lot of research on the subject called knowledge distillation, where people try to have this heavy network teaching smaller one, and there are some other works where people replace big chunks of these trained heavy models with lighter one. But anyway, image augmentations can slightly help with this. What do you want to see and what part of the slide is important? So there are like two networks depicted here. Both are kind of heavy, but still. So amoeba C and amoeba A. Number of parameters in both of them there's a difference of 3 times. Yeah? Like 150 versus like 270. And what's happening here? If you can like compare second row, it's like light network with augmentations, or third row with augmentations. In the right column, you see 83.88 and 83.19. Basically, accuracy is very similar, is not the same. What does it mean? It means that you have lighter network that achieves same accuracy. And lighter network typically means less you can deploy to production, and also it means that for convergence, for training, maybe you'll spend less time on the compute, so kind of still useful. Okay, this again, augmentations to improve robustness. I really like this work. What happened here? It's one of the papers, good papers in deep learning, when authors trained 0 networks. So people a lot of typically complain, we don't have hardware these days to train something cool, to be research breakthrough. Good enough, this is an example. They didn't train anything. What did they do? They took some pre-trained network that are good, like state-of-the-art, shared publicly on the Coco dataset. And they took some image, and on the left you see like Jon Snow and dragon, sure, like person, bird, kind of works. What they did after this, they took these images and they corrupted them, played with brightness, added some Gaussian blur, added something like this, and trained this existing network. And what they realized, that even small changes, small deviations from the original data distribution in terms of brightness, in terms of contrast, in terms of something else, and your network like not working well. What does it mean? Your network is not robust as much as you would like it to be. So what the solution for this? You apply more augmentations during training, it becomes more robust, life is good. Yeah. So this is a good example. Again, medical imaging, self-driving, anything else. Okay, so what types of augmentations do we have? There are like few types of augmentations that one can think. First type, most widely used, pixel level augmentations. What is happening? Your target is input image. So if you have some image, you can play with pixels. I don't know. If you add 1 to every pixel to the parrot, it's still parrot, but pixel values are different. So from your perspective, if you add 1 pixel to everything, you will not even see the difference as a human, but your network will need to adapt to this. And you can go harsher to this. So on the left, there are some examples of like brightness, contrast, augmentations. Converting to grayscale may provide value. There's cool augmentations I learned when I worked on some problem in forensics about, there's apparently good transform called HPEG compression. So in the field of forensic and computer vision, apparently there's like big field of research that I didn't know about, where people need to identify, was HPEG compression applied to this image or not? I would never guess about this, but still, I learned something. And right now, for many problems that I solve, I apply random like strength of HPEG compression to the input images. It's non-linear transformation. It's not like slide shift or like, brightness contrast. It's more advanced and it definitely adds value. And there was a lot of, also like kind of like people started using this in machine learning competitions, and I hope industry will, academia will catch up and will get there. On the right is my home city. I work in self-driving. Some weekend it was raining. I was like tired and like, or maybe not tired, full of energy. And I decided to do something cool. So I added this type of the transforms. Top left corner is my home city, and on the right is a bit of rain, on the bottom a bit of sun, and bottom right corner is a bit of like fog. Again, it may look unnatural, but I was told that in some problems where people need to detect something on the web cameras on the streets, these transforms will be useful to improve the quality of the models. And on the bottom, there are examples of these transforms that we have in, my collaborators and I have in our library, and plenty of weird of them, blur, channel dropout, some motion blur, etc., etc. Okay, there are like another thing that is not that much useful yet, at least I didn't see. I've seen paper that claim that it adds value, but I didn't see any. Basically, none of my friends told me that it worked for them. Yeah. So what people are trying to do, augmentations with GANs, more advanced, more nonlinear, and pretty cool. So on the left column, you have original image. In the middle, you have some other image. And on the right, you have original image one that's on the left, in the style that you have in the middle. So again, use case, let's say you have some images that you collected during the day for self-driving, and then you need to, adapt them to the night. Okay, let's take some theoretical situation. Let's take some night images, let's merge, let's use this trick, and you get same images that we detected had for the daytime, including labels that we have on them, and then it's in the night. So it works in theory, and there is I've seen people raise money for their startups for building this. The value is unclear yet. But I hope with time it will work, because again, you can avoid labeling data and use this trick and generate a lot that is natural and may help your models. Okay, spatial transforms. I worked a few times with satellite and aerial imagery. You do this from the top, and you can apply a lot of transforms. They may not even change your pixel values, although of course you can combine with the previous one. But again, let's say you look from the top, there's a building. You rotate it by 90 degrees, it's still a building. Then you flip it, it's again a building. So for you, it may look the same, but for the network, same distribution, life is good. So these 8 transforms are mandatory when people work on satellite imagery, but of course there are plenty of them. For example, this one. On the right, there is grid distortion and elastic transform. Worked really well for me for medical imaging. I mean, you wouldn't apply elastic transform for, for your face, because, it will get corrupted and may not necessarily be good for your model. But if you're talking, and maybe again, corrupting this hair is not such a great idea, but if you're talking about some cells in your body, you take some cell, you apply this transform, maybe expert will distinguish them. For me, there is no difference. But for the model, it improves the robustness. Again, spatial transforms can be applied not just to images, but also to key points. On the left, there's this nice cute fox. And if you can see, there's some green key points. So when you apply transform, flip, rotate, scale, they also should be rotated in sync. Again, and on the bottom, crops, and so a bunch of them that can be applied. Okay, so let's talk about this. As I mentioned, I have some experience in machine learning competitions. Overall, I like getting knowledge from competitions. So when I face some new projects at work or in my free time, what many people do, they start looking for relevant literature. Maybe read some 10 papers, try to figure out what's happening there, trying to implement this in the code. I prefer to do it in a slightly different way. So if I'm facing some new problem that I never faced before and not comfortable with, I look for machine learning competitions that are similar to this. Why? Because when people work on competitions, there's leaderboard. There's who is doing best, who is doing worse. For many competitions, it's mandatory for winners to share their code publicly. Again, I can step on the toes of the giants and go from there. And again, if you read the papers, many of you know, every paper claims that they're not like everyone else, they're state of the art. Which of them, what is true, what is not, it's hard to judge. Competitions in some sense, of course, there is also some bias to the data set, but still they work better. So there was competition Urban 3D. First place, my buddy Alexander Buslaev, who's also co-author of this library that I mentioned at the beginning, and then trying to promote maybe in this talk. He got first place, and from the he lives in Minsk, Belarus, and from the money that he got as a winner, he bought an apartment there. So it was good investment of his time. So the task was instant segmentation. On the left is, you can some aerial imagery, and there's some buildings there, and you need to, on the pixel level, to identify which pixel is which building. So he used optical distortion, grid distortion, flip, shift scale rotate, transpose, hue saturation value, and few other transforms. Ones that I mentioned the previous one, and few about pixel values. And again, first place, tough competition, apartment in Minsk. Okay, second one, top quarter, road extraction, routing challenge. First place, again, my friend Alexander Buslaev. I don't know what was the prize and what he did with this. But again, the task was, you have satellite images and you need to detect roads. And not roads on the pixel level. You need to detect roads as a graph. So let's say if you have some road and you didn't detect some, 3 pixels in the middle, so it got disconnected, it was bad for the score. So you need to detect real road network. I don't know, it was China or some other, countries where it's not that well. Maps maybe are not that great in the regions when they were facing. Task semantic segmentation, again, top view images, flip, transpose, shift, scale, rotate, and shifts in the pixel values in the HSV space. Again, helped him to make him more robust. Another thing that I like to add about SpaceNet challenges that organizers are facing, what they like to do, they like to give you train set, Las Vegas and Paris, and your test set is somewhere Moscow and Shanghai. And clearly, you still can identify that this is building or this is road or this is something else, but your network may be confused because it's definitely different data set, different distribution, and to be able to work there, you need to apply augmentations and some other regularization techniques to make it more robust. So this SpaceNet challenges, it's a good example of how it should be done to make your network work. Okay, this one. This challenge was 3 of us. It was me, Alexander, and Artem. Artem right now is in Facebook AI research. I don't know if this result helped him. He's a smart guy even without this. But still, we spent 10 days. We got to the first place. The task was semantic segmentation. You get images of the cars, and you need to subtract background. Basically, semantic segmentation on the binary level, and we got absolutely pixel level accuracy. It was labeling was so good for this data set, which is typically doesn't happen. And our models were so good and augmentations kind of worked. We got, I don't know, if you think accuracy, it was IU, but still 0.997. So it was really, 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 really accurate. So semantic segmentation, 3 of us. As you can see for these images, vertical flip probably is not a good idea because cars upside down, it's questionable if they're kind of related and your network may get confused, but horizontal flip for sure. Playing with scale a bit, definitely. Brightness, yeah, brightness kind of makes sense because some are just more bright, less bright, reflection from the car, still brightness, and some shifts and HSV. This one I like. This again, Alexander and a couple of my, Selim Seferbekov and Viktor Durnov, I also know them. It was a challenge called Data Science Ball. It was almost 4,000 participants. You needed to detect, do this instance segmentation on and detect these different cells. And the cool part of it, organizers told them, we will not give you test set, it will be released later, so you will not have access test to this, but we can guarantee to you that it will be different. Different in terms of data distribution. And so many teams in this problem, they were affected by the shift. So when they evaluating their models on the train set, they could be at the top, but then test set was released and situation changed. Some teams dropped 1,000 places. So overfitting was an issue. But yeah, these folks, they were first on the public leaderboard and first on the private, and at the bottom is the list of the augmentations that they applied. And this is 3 lines. Rotations, distortions, pixel level, transposition, some motion blur, everything else. They told me that during training, so typically, when you train some data set, your train loss is below your validation loss. Validation loss is bigger, train loss is smaller. For this problem, it wasn't the case. Due to this aggressive regularization, due to this aggressive augmentations that were applied only to train but not to validation, the train loss was significantly bigger than validation one. Still, first place, they got DGX. First DGX, this device with 12 GPUs and everything like this, and 50K in prizes. So yeah, pretty cool. Another cool story that I like about this, there were some people from academia that wanted to publish their state-of-the-art research on this data set. And they trained some model, got some ideas, did some ablation study, wrote some paper, everything is great, and then they submitted this to some journal or some conference, and it was rejected. The reason for this was because their score on this data set was lower than for these folks. Okay. Next one, inclusive images, similar. Here I just want to mention what was happening there. Multi-label classification. I think it was organized by, this competition was organized by Google. You take some image and you need to say what's happening there. Is there food, or maybe it's sport, child, soccer, training. Basically attach some kind of labels that later on can be used for sorting or search for this type of the tasks. So my friend Pavel got first place. Again, train was really different from test, and organizers said this by default. We get this from one distribution, another from. This is from train, this is from train and test were coming from different sources, different distributions, and different geographies. And organizers, as I've said, it was Google, I believe, their point of this activity was to see how much models will drop in accuracy when you shift from one geography to another, and it looks like it wasn't that big. Again, augmentation, scaling, rotation, Gaussian nose, medium blur, brightness, HCV. Again, medical imaging, semantic segmentation, what transforms will naturally come here. Horizontal flip, gamma, brightness, elastic transform, grid distortion, optical shift, scale, rotate. Again, first place out of 1500. Aunur, I don't know him personally, but still, first place. Okay, Thank you. So in this talk, I tried to describe you what image augmentations are, how can be useful for competitions, and showed some examples of this, and how they can be used in industry. This library that I mentioned in the beginning, it is used in production in Lyft to build self-driving car. I got approval from in-house, our team, to get this something. And I was also told from some folks from Snapchat, Facebook, and Google, they also use it internally. I mean, some people, I'm not saying all Google, some people, because good library, good technique, but I cannot push my friends enough to get approval from their manager to make this information public. Still, okay, if you're interested in our library, feel free to use it. If you want to contact me, here's my LinkedIn and Twitter. And now, I don't know if you have some time.
You do. Questions?
I do have time.
Yes.
Questions?
Questions.
Okay.
First question is, first of all, thank you very much for this fantastic. You mentioned three methods in terms of medical images. One is augmentation by gas, and augmentation by spatial augmentation.
Okay, the question is, let me repeat this for recording. For medical imaging, what type of augmentations exist? Medical imaging is not specific in any way, like transformations that can be used for overall types of the transformation that can be used for any other type of the imaging can be used for medical imaging. What type of transformations can be used overall? We can, let's say you need to do binary segmentation like this. Like this, binary segmentation. Let's say you, like on the left is your image and on the right is your target. You can play with your image on the left with pixel values. I mean, make it darker, make it brighter, maybe use guns, maybe use something like this. Purely on the image, your mask is unaffected. So pixel level transformations, they affect only your image. Whatever, only pixel values, it's one type. Second type, spatial transformations. As I've said, let's say we don't want to affect pixel values, but we want to zoom into some region. Or maybe we want to flip, or maybe you want to rotate by 5 degrees. So in this sense, you need simultaneously affect both your image and your target mask for this type of the task. So these are spatial transforms, one that affect both image and mask in some spatial way. Yeah? Geometric way.
So here's my question, Gaurav. So at the end of the day, this is unlabeled data, it's pretty much dark data. Right? I need the ground truth to have the data.
No.
In terms of saying that, in your opinion, which is the best way to generate synthetic images to make sure that we have the ground truth as labeled data, and once we have the labeled data, how do I apply the internal model on top of it so that the accuracy increases? And if there are any concepts that, in your opinion, would be applied to make sure I take these images and see that these are the good images, labeled images now, and if I take it, now I can put my classifier on top. So, which is the best method to gather the spatial or image to generate the data, and we have point of view on labeled data.
Okay, so answer, first of all, augmentations, when you apply, let's say you have this image that I'm just depicting on this, like on the presentation. And on the left is your image and on the right is your target, right? So for this image, you have ground truth, right? If you make this image twice darker, what happens with your target? Nothing. It's still your target. So what I'm talking about with these image augmentations, your target is not affected. I'm saying, so these augmentations are used to generate labeled data. Following? So or let's say you flip this image horizontally, and then you flip this mask, your target, horizontally. It will be valid target for your original image. So all these transforms that I was talking about, they have ground truth data by default. That's the point of them. To generate synthetic like this, like augmented data that is labeled, and this labeled are correct and they correspond to the original train set.
So with elastic grids, you're changing the original set, right? Elastic grids.
Okay, let's look at the elastic. So if you do this elastic transform, if you need like to distinguish if it's like person or maybe like, skull of the person or dog, it doesn't really matter, your label is still the same. If you're talking about like mask that corresponds to this elastic transform, yeah, let's say, your question is like on these images, on these X-rays to identify pixels that belong to the eye. You'll have your image as your input and you have some mask as your output, yeah, where pixels about eye are labeled. If you apply elastic transform to your original image, of course you need to apply exactly the same elastic transform to your target mask. all these transformations should be applied to your data in such a way that ground truth stays valid. That's the point of this. We're extending ground truth without doing any assumptions, without doing any semi-supervision tricks. No distillation, directive learning, nothing of this. You have the data, you apply transformations, instantly you get extended train set.
Okay, we are running
Yeah,
a little behind.
you can ask
This
me.
gentleman is going to have a call. So ask your questions
Okay.
later. So can I have that clicker?
Clicker.